Hey, the first thing I like to talk a lot on the files and continuing what we did on last Thursday. The first thing I like to talk about is homework assignment number one. I provide a little bit update, which is talk about more about the part two. So let me just briefly mention what are we doing in part one and what we're doing in part two. So in part one, it's 7%. I mean, remember the homework assignment on one counts 10% of the whole semester. So 7% is about how do you write a program called EE1520 heal.c and such that it will provide the healing function for the result of EE1520 break.c. If you go to the GitHub directory, I upload a few things. Let me just get back here. I pretty much upload, I think I'll upload everything. So I have, I want to view all the file. Yes, thank you. There is a few things. First, for homework assignment number one, you need to have the makefile underscore break heal diff. Okay, that's the makefile specifically for homework assignment number one. You need to change a little bit when you want to compile E1520 underscore heal.c. You need to do that part, but just like you know, you should start it from there. And then we have the program called my break.c, my diff.c, my heal.c, which I show you how you can develop this set of program to break a file into pieces and then heal the back. So the demonstration of this three program was presented last week. So if you missed that for some reason, go to the YouTube to get that. Okay, that's the thing. So for homework assignment number one, what we need to do is you need to take this program E1520 underscore break.c, which I will show you a demo. And what you need to do is you need to write a program called E1520 heal.c. So this is a somewhat different way of breaking it. I will show you a demo so you will know precisely what's the difference. And if you look at that, by the way, there was another thing is the homework assignment number one. This document is on GitHub, is the Microsoft Word file for homework assignment number one. So you can download this file. If you need, if you cannot download, let me know. Okay, you should be able to download because that's something which we want to encourage you or force you to do GitHub as much as you can. Okay, and that's the first part. Let me get back to this document. So you can see that for part one, I told you that I'm giving you a program called my break.c and my heal.c. They kind of work together, which one is breaking, one is healing back. Okay, two-way street. So this homework assignment, we're going to do this part, I'm going to say now this is what you need to do, is that we provide another version of my break.c called E1520 underscore break.c, which is the one already in the GitHub. And the difference is some of the parameters, such as chunk number or chunk size and chunk prefix, will be recorded in what I call a meta file. Okay, in a meta file, which is a configuration file. So when you heal it, you should just read the parameter from that meta file. So otherwise, they're the same. They're doing the same thing, but I'm actually relying on the meta file to do that. So I want to tell you that this program, if you understand how my heal.c and my break.c were implemented, then when you implement E1520 heal.c, it's fairly straightforward. It's only about where you get those parameters. So instead of make a long story short. So with my heal.c, you can see that you need to provide 4 arguments: source to ID CSV, my prefix, the chunk size and the number of chunks. You need to provide 4 arguments in order to do that. But with E1520 heal.c, you only need to provide 1 argument, which is the name of the output file. The rest of the parameter, including prefix, including this, is already inside the meta file. Okay. All right. Good. So so let me just do that. So that's the one thing. And then I just want to tell you the grading policy. So the 7%. So there is a 4%. I want to make sure that you will be able to generate the result, the heal file, and without any trouble. I'm using the diff program to see if they're the same. And also I want to make sure that your program is compiled and you have the correct make file to get it to work. Okay, so that's basically count 4% out of that 7%. Wait a minute. There is a 1%. Okay, I'm sorry, I make a mistake. If you have a diff correctly, that's 4%, but I will give you 1% extra. So this should be really 5%. 1% for you have a make file correctly, your program can compile correctly, those things count 1%. And then there's a 2 extra 1%. The other 1% saying that, well, if you have a one of the chunk that was missing, I want you to my heal or whatever, the EE1520 heal.c, they will detect that if you have a chunk that's missing. And the other thing which it will detect if the size, the chunk size is mismatched. For example, I'm expecting that each of the chunk is 1 GB, but then the chunk I'm reading with the same name is only about 1 MB, which is there is a difference between chunk size. So number 2 and number 3 each counts 1%, is basically ask you to provide the detection mechanism for this 2 kind of error. Okay, so that's the part. And then the part 2 is really just provide you a question, but you may provide a program. If you do a program, I mean, it's given that you're going to get 3%. You're going to get all the percent. But if you don't have a program, then you basically talk about concept. So it depending on how your presentation about the concept, you might get 3%, you might get less. Okay, so there is a program. So let me tell you what this is. Okay, let me draw a picture. I want to turn on my PowerPoint. I'm going to insert a new slide. So let's assume that this is a chunk. And this chunk, let's assume is 1 GB. How do I make it smaller? Let me see. Okay, so I'm going to put it in the middle. Okay, so this is a chunk. I'm assuming my chunk size is 1 GB. It could be anything you want. You can specify when you break it, but I just followed the example I had last week to have 1 GB. So essentially what I did was, let me show you. Let me actually do it this way. So here I have about 13 chunks. Sorry. I have 13 chunks. And each chunk is 1 gigabyte. But I want to say because my last chunk is usually smaller, so I'm actually going to shrink it a little bit. No, I cannot do. Oh, I can do this. Good. And the last chunk, let's assuming is a 0.6 gigabyte. Okay, so that's the last chunk. So think about the program we're doing is we have a file which is about 12.6 gigabyte. So the total file size is 12.7 gigabyte. And when I separate my file into different chunks, the first 12 chunks should be 1 gigabyte, and the last chunk should be 0.6 gigabyte. Okay, so that's what break is just breaking into this. And so then you can actually store each of the chunk into your USB FAT32 file system, or you can actually store any way you want. Okay. By the way, to separate is very important when you want to transfer a large file, such as a large database. I mean, to be honest with you, the past 4 days, I have been transfer a database about 1.4 terabyte. And I'm actually going to transfer, you can imagine 1.4 terabyte, I'm actually transfer from UC Davis to NCKU. I have some research data I was putting there. If I directly transfer 1.4 terabyte, then in the middle of transfer, if something goes wrong, I'm not sure whether the file transfer will be able to recover to the point where I ended. By the way I do it is I break that using exactly my break and my heal. I break that into multiple chunks and I transfer them one by one. And it took me 6 days to transfer everything because it took a long time. It's a huge file, and the internet speed between Davis and NCKU is not that fantastic. So it took me a while to do this transfer. So this is useful when you want to transfer a big file that, because in the middle, something will go wrong. And what I can do is, for example, if I transfer 6 chunks successfully, in the middle of the 7 chunks, I actually messed up. So when I restart, I would just start it from the 7th chunk and go on. So this is very useful when you talk about this kind of unreliable network environment. You want to do this. Okay, so this has been the answer we're doing. So you can see that there's a few parameter you need to worry. For example, you need to know the size of the chunk, which is 1 gigabyte, and you need to know the number of chunks so you can heal them back together. And the other thing, you need to know the name of each of the chunk. Okay, so that's the 3 information: the name of the chunk, the size of the chunk, and the number of chunks. Okay, so those 3 things. Okay, so I'm going to show you demo a bit later, but I want to talk about part 2, which I presented here, about this one. Okay, I use a lot of description about what you need to do, but let me actually use the PowerPoint slide to discuss with you conceptually what I'm asking. Okay, so assuming this is a movie, this is a movie of 12.1 gigabyte. So in order for you to watch the movie, or for me to watch the movie, or for you to, if this is a database that you want to access the data, or if this is a large language model that you want to access a generative AI foundation model, pretty much what we have done so far, we're saying that, hey, you have to not only get all the chunks, but you need to heal them together. And then you can start using the file. For example, you want to watch the movie and you have to get all 13 chunks and using the My Heal program so you can put things together. Okay, now I'm going to talk about something different. What I'm asking is that, okay, assuming this is the file, this is a complete file about this duplicate. Okay, now I'm going to say this. Assuming I want to, oh, not this one. I got the wrong one. Which one? Not this. Why is this? Where is my shape filter? Is here? No, not here. Suddenly, where do I? Wait a minute. Why I suddenly lost a important feature? Forget it. I'm going to do this. Let me see if I can do this. Okay, anyway, I'm going to use the yellow. That's fine. I'm going to use yellow. Okay, okay, now I'm going to ask you a different question. So assuming this is a movie and the only portion of the movie I like to watch is chunk number 1 and chunk number 6. Okay, that's obvious, right? I don't have to watch the whole thing. I want to watch only chunk number 1 and chunk number 6. I mean, similarly for database, I don't need to access every single column of the database, but I want to access the database, the portion of the database only in chunk number 1 and chunk number 6. Okay, so in other words, I'm asking, why do we need to gather all the chunks, all 13 chunks, while we only need 2 chunks? Why can't we immediately use the file before I actually spend 4 days to download 1.4 terabyte from UC Davis over here? Why can't I start doing the work? So in other words, what I'm asking is that if I want to implement this idea about just getting exactly the chunks I need without getting everything, and then I can start using it. And how do we do that? So I have a 2 question. I mean, what do you think in terms of the concept? How do you think that you can actually realize this concept? And then you can actually talk about the programming side. Sorry, the programming about how to really build a system that's actually based on this. Okay, so that's by the way, this is a very, I would say, very advanced question because it's not just programming, but basically it challenges you to understand how you can manipulate information because programming is all about how do you handle information. Okay, so how do we do this? So let me give you a hint. You can actually mention this in your answer. Remember last night we talked about a concept called file with whole or sparse file. I don't know if you forgot what I said last time, just rewind your YouTube video to watch what we did last Thursday. Let me actually show you what is a file with whole. So file with whole looks like this. Is that this one? I would just get rid of this. This way. Wait a minute. Okay, so here's a file with hole that I show you under this program called sparse test.c. I will be able to randomly pick 5 locations to write a few bytes. So here is a concept called file with hole, meaning that it's possible for us to create a file that's only certain location that has data, has content. And you can decide, let me actually go back to the code. It's already on the GitHub. If you look at this code called sparse test.c, which we went over last week, if you look at this, we have a function called, let me move up a little bit. So this function basically create file with hole. You provide a file descriptor, which is a number regarding which file it is, and the position and the character, the number of string that you want to write it there. So essentially what we did is position is move to a particular location, and then I'm going to write certain number of bytes onto that location. So, I mean, if you hear what I just said, let me repeat what I said. I'm going to type it in here. Is that for a given file, we will move the rewrite head to a position. And then we write a number of bytes. So essentially what the concept of what we call the file with hole is that we don't have to write the file sequentially. Meaning that if you have a huge file, you don't have to write the file from byte number 1 to the last byte. What you can do is using lseek to jump to a particular position and start writing. So if you look at this, I'm going to write it this way. So I'm going to move to the beginning of the first chunk and the beginning of the 6th chunk. And then write 1 gigabyte each. Okay, so the picture down there is essentially what we just did with the file with hole. So essentially what you can see is that, okay, when I access the file, I'm not accessed sequentially. So using lseek, using the sparse test, I can move over here to write, I mean, this is the beginning, right? I can actually move, and then this is 1 gigabyte. I'm going to write that 1 gigabyte, starting from byte 0. So byte 0 is the first byte of the first chunk. And then what's the position of the 6th chunk? That means I have to skip the first 5 chunks. And how many bytes I need to skip is the size of the chunk, which is 1 gig, times 5. And if I skip that, then that's the first byte of the 6th chunk. And then I start writing 1 gigabyte to that chunk. And then I will be able to create a file with hole, looks like this. So in other words, if I can produce this, by the way, I already, if you understand sparse test, you should be able to write a program to do this. If you already create this one, then that's no problem. You can actually directly create a file that's as if you have the whole file, the only 2 chunks available, because you know you only need those 2 chunks at that moment. And this is very flexible. Say after 2 days, you realize you need chunks number 11. Then you do the same thing. You insert another chunk into this file with whole, and then you will be able to do that. So this is an interesting concept. Let me get back. That's what we want you to do. Sorry. That's basically I want you to do to a high-level design or description. Remember, I said hint, look at sparse, test.c regarding how we can start using the file without having to heal all the chunk first. So I'm not healing all the chunks, but I'm actually healing specific chunk that I'm going to use. Then I can actually start doing that. So basically, if you can have I mean, you can just tell me, but if you have a program which is based on Spark's test.c, you can actually demonstrate the idea. Then you present your, I mean, this is my preference, just be honest with you. The best way to present an idea is using a program. I mean, in the context of EE1520. Okay, the best way to present an idea is to write a program. I want to challenge you to do that. If you can do that, then you got 3%. I might actually give you a bonus of 0.5%. Okay, that means you potentially get 10.5. But if you don't feel comfortable, then having a design, that's fine. Okay, and then we're going to do interactive grading. I want to see your demo. And I just want to let you know, it's a very important thing about this homework assignment is that, did I say something over here? Yes, I do. I do say this. This is my main requirement about the homework is that when you turn in your work, you can actually reference to some online resources or my reference code or even somebody else help you. You can actually have other people's code in your work. That's fine. But you need to know what it is. You need to know. You need to explain what it is. If I ask you a question, you have to demonstrate you really know the code. Okay, because I feel that's the most important thing. I mean, I want you to know your own code. Okay, all right. So that's pretty much the homework assignment number 1. I'm going to demonstrate EE1520 break.c, but before that, I want to do participation. Okay, so as we mentioned, we have this participation credit. I'm going to check on this. I'm going to run. Okay, I'm going to run the server. Sorry, I haven't started running the server. Oh, I know what I'm going to do. I'm going to check today. Today, I'm going to check for New York Times. Let's see. New York Times. The first article of the New York Times. Greenland. Okay. So I'm going to look for Greenland. All right. So now I'm going to go back to my code. And I'm going to modify this passcode. Where's my passcode? No, I got to the wrong place. No, not this one here. Okay, here I said this was last week. I forgot what it is. So now I'm going to do this. So today it's going to be Greenland. Okay, I'm going to run the server. Okay, server dot slash E1520 server. Okay, the server is up. You can try. I'm going to modify my client CPP. And I'm going to modify again in this place, change from Israel to Greenland. Oh, sorry, I make somebody else student ID. I should remove this. You can see this part. Okay, and I'm going to run it. Yeah, I'm successful. Oh, fail. Why is fail? What did I do? I'm sorry. What did I do? See, that's the beauty about programming. You never know what will happen until you run the program. Okay. It was Greenland. Did I put a space in between those two words? Okay, let me check. What did I do here? I thought I did the right thing. This is Greenland, right? Anybody successfully? That's interesting. Let me actually see my server. What happened? Oh, you know what? I'm sorry. This is not a problem. This is because I haven't killed all my server. The previous server. I must have another server running. You see, this is the server is still running and it's probably occupied the resources. Okay, now I know. See, this is interesting. I forgot to turn off the server from last week. So therefore, the same port number, it will went to the previous one. So now, so this is interesting always about distributed programming. You have to see that which is the service. Now it's successful. Okay, good. So it's Greenland. You should get your stuff. Okay. Okay, I got a Greenland, so I'm going to teach the rest of the stuff. You can play around with whatever you did. Okay, I'm going to demonstrate I'm going to get rid of this. This is confusing. This is also confusing. Hey, wait a minute. Okay, I'm getting rid of this too. So now I'm coming back here. Okay, this is the directory. Basically have this my break, my heal.c. Let me make everything. Make file, break, heal, clean. I want to clean that, and then I will make it. Okay, you can see that I create in this file, I make my break, my heal, my diff, and E1520 break. Okay, so let me choose one file. I will use my PowerPoint. This time I'm going to use my PowerPoint 4 as the file. I'm going to break it. So I'm going to do my break. So my break, I have the source. The source is NCKU CSII 004. Okay. And then the prefix, I will call it EE15. I'll call it my prefix. My prefix, just anything you can put there. And then the chunk size, let me put the chunk size to be 256, which means 256K. Maybe I should put a 1024K, 1 MB. Okay. And then that's it. So I can put it. So you can see that I make each of this 1 MB. I have 12 chunks from 0 to 11. So when you do my heal, you have to do / my heal. You have to provide 4 arguments besides the command line. You have to put source. Wait a minute, what happened? Okay, I'll use this one. Thank you. Okay. Oh, this one's okay. Thank you. Thank you. Thank you. Okay. Okay. Good. Okay. So you can see that I'll just speak louder. Okay. We only have 9 minutes. So here I have to provide 4 arguments. Source. Oh, this is why we need the signal processing. This is unreliable, very uncomfortable. Sometimes it works, sometimes it doesn't work. Okay, so we provide source, prefix, chunk size, and chunks in order to do that. So that is a one design. So now I'm going to break the same file. I'm going to use EE1520 break. Sure, thank you. And it's a still parameter, but my prefix, I will say my prefix 2. Okay, now I create my prefix 2. I create those files. But I also generate a file called my prefix 2.meta. See, this is a file I create. And look at this file. I basically have 3 arguments. The first argument is number of chunks, 12. And the size of each chunk is 1 MB. Okay, believe me, that number represents that's 1 MB. And then the third one is the prefix, which is my prefix 2. So that's okay. That's okay. It's okay. We're almost done. So with this 3 argument that I can actually write a program called EE1520 heal.c, which is reading this argument to heal them back. I don't have to kind of remember all this numbers, such as the size of the chunk and number of chunks. Okay, so that's basically what you need to do. So when you heal it, I'm actually just typing it. If you have a program called EE1520 heal, then you're going to provide a few arguments. Then I would say the first argument is still NCKU CSII 004.ppt and then pptx.copy. Okay, I usually want to create a file, which is the file name is different from the original file because I want to make sure you don't overwrite your original file just by mistake. Because you're doing development, sometimes you can do that. But the second argument you need to provide is my prefix 2.meta. Okay, if you provide this interface, then essentially your program should be getting the information, the meta information from my prefix 2.meta, and then you will be able to do that. Okay, so that's what you need to do for assignment number 2. Okay, so now I'm going to show you something really interesting. Well, some of you will say, well, whenever Professor Wu says something very interesting, is usually a headache. Yes, it might be. Okay, so let me actually check the other file, which my guess is ttt.cpp. No, S star dot C. Let me actually take a look which one. I have to look at their timestamp. Not HBO. Ah, F-write test. So I'm actually going to give you a comparison between F-write test.c and sparse test.c. Okay, I'm actually showing you two different programs. I know some of you are busy with participation. You can work on that a little bit later after class. I will keep my server open for a while. So in this program, the sparse test.c, I'm using lseek and I'm using write. I'm using lseek and write. But the fwrite test, I'm using fseek. And I'm actually using fprint. So let me do this. I want to do somewhat different. I'm going to cp sparse test.c to non-sparse test.c. Okay, I will show you what I did with a non-sparse. Okay, so I'm going to do this, but I'm going to change this to file star F. And over here, I'm going to do fseek. Let me see. I am sure X. This is what I call, what was the file? Fwrite test, right? Fwrite test.c. Let me see. What I did here is, yeah, using fseek. Using fseek, which is the, what is that? Is that underscore F? Yes, underscore F. And then the position and seek set, the same thing. And then I'm going to copy, I'm going to do fwrite. Can I do fwrite? Yeah, okay, I'm going to do fprintf. It's easier. Fprintf minus F, and then I'm going to write %s, and then string. Okay, this is very similar to what I show you with sparse test, but I'm actually using fseek and fprintf instead of lseek and write. And over here, I'm going to do file star F, and I'm going to do F open. I would say file without hole. I think what I did is, sorry, just give me a second. Let me get, okay, yeah, I got this. So this one is, I will call it dot slash, and then I'm going to put, the interface is a little bit different between this two set of call. Okay, and then I'm going to get rid of this. And I'm going to create file with hole. I'm going to write, is that F? Yes, it's F, random, and hello. Okay, I'm going to write it out this way. It's almost the same as this one. Let me do a GCC non-parse.c minus O non-parse. Oh, make a mistake. Close. So this should be F close. Okay, so I'm actually going to generate if you remember what we did, let me actually compare this two. One is sparse test.c, GCC sparse test.c. I'm generate this to sparse. If I run the program /sparse, and I have the program, the logical file size is huge, is 1.6 whatever terabyte or something. Sorry, 1.6 gigabyte. And then if I do du, it's about 49 megabyte. So even though I'm creating a virtual file with 1.6 gigabyte, I'm actually only use 49 megabyte when I use disk usage. But now if I run the other program called non-sparse, I'm sorry, I make a mistake. Okay, so I'm creating another file. Let's actually look at this. So I create another file called file without hole. The size is almost the same, file w hole. But now I actually do a du minus h. Really? It's the same? Huh. It was giving me different answer while I was there the other day. But anyway, this is two different way. I'm going to stop here and you can continue to submit. I will see you on Thursday. I'll figure out what happened, the last part.